In this lesson, we're going to be talking about the inverse trigonometric function. In a sense, the inverse trigonometric functions are just like the undo buttons for the normal trigonometric functions. However, because these undo buttons are actually going to be functions, some conditions are going to apply. To explain to you how these undo buttons work, and to explain why I'm saying conditions apply, let me start by actually drawing on the trig functions and their inverse functions. As we discussed in an earlier lesson, these three functions are called the trigonometric functions. All three of these functions take in an angle that we call theta and use it to find a coordinate. From this coordinate, cos returns the x value, sine returns the y value, and tan returns the gradient to the x-axis. Now each inverse function is meant to be paired with an original function, and it's meant to undo the action of that function. For example, given an x-coordinate, arccos will try to find the original angle you put in, which should come out over here. Similarly, given a y-coordinate, arcsine will also try to find the original theta you put in. Similarly, given a gradient, arctan will try to find the value of theta that you put in as well. So whenever you see an a in front of the function name, you know that we're dealing with an inverse function. So that you totally understand how this works, it would be a really good idea to show you a particular example. So let's go ahead and hide the sine and tan paths a little bit. Pretend we started with a random angle. I'll just choose 3 pi on 7. I've also written it without the pi at the bottom just for your convenience. I'm going to bring out the calculator so that we can substitute this value directly into cos. Now the first thing to do is to make sure that you've set your calculator to radians. Once you've done that, you can type cos 3 pi on 7 and get the answer. We can copy this onto our diagram as well. Because this number is just a coordinate, it doesn't actually need a unit like degrees or radians anymore. Now let's use our calculator to figure out what the arccos of this number is as well. Notice that we get the exact same value out that we started with right at the beginning. Now if you're struggling to find arccos on your calculator, I just want you to note that some calculators write this differently, and I'll talk about why at the end of this lesson. The alternative notation is this cos to the power of -1 that I've shown here. Now if you've been using exact values this whole time, you can go ahead and divide this number by pi to get this original number that we started with here. To actually make this work, you'd have to type in all the digits, which is what I mean by this ellipsis. At this point you might be thinking, well, we put in some number, we put it through cos, and we got back the original number. What do you mean when you say conditions apply? Now all I need to do to convince you that this doesn't always work is to change the number that I put in. So let's go ahead and try 11 pi on 7 as the input this time. Now I'll just use the calculator to get the x-coordinate, and then I'll undo it to get the theta coordinate as well. Now I hope you can see we have a little bit of a problem. You started with 11 pi on 7 radians, and now you have 3 pi on 11 radians, which is not what you started with. So clearly, arccos does have some conditions applied that we should know about if we're going to understand it properly. Now if you look for them, you're going to find cases that don't work on all three of these functions. So to properly understand what's going on, we're going to have to look inside of them to see how they work. I'm going to draw cos and arccos again, but this time I'm going to draw them with the lid open so you can see how they work. Now remember that we put in an angle of 11 pi on 7, so we need to draw that on this first axis. After this, we go ahead and intersect this ray with this circle to find the point of intersection. Cos then goes ahead and finds the x-coordinate and returns it. We usually write x as cos theta. Now we can investigate arccos as well. But while we do this, we have to remember that it can't see what went on inside of the original cos function. All arccos knows is that the input x-coordinate was 0.22, and it wants to try to figure out what the original angle was from that information. So we went ahead and marked on the line that shows x equals 0.22. But the really big problem is that you can see that it intercepts in two places. Now this is actually a problem because arccos is a function, and functions can only give you one output, so it has to choose one of these 2 points, and in this case it's going to choose this one. Now if we go ahead and draw on the angle, you'll see that it's clearly different to the angle that we actually started with. Now if we measure really carefully, we'll see that this is none other than the 3 pi on 11 that we got. We can also go ahead and write this as theta equals arc cos of x. Now we know that x is just the same thing as cos of theta, so we can go ahead and make this replacement as well. So this kind of tells us that whenever we see a cos next to an arc cos, we can cross them out, but conditions apply as we said before. Now I hope you understand why things can go wrong, so I'll go ahead and get rid of all the things that I don't need. Now I'll go ahead and shrink this, and then I'll make copies of this picture for sine and tan. Let's start with sine first. It just goes ahead and takes the y-coordinate and spits it out. Now unlike arc cos, instead of getting an x-coordinate, this time we've got a y-coordinate. So we need to mark out the line that gives us a particular y-coordinate. Just like last time, there were 2 possible points, and we always prefer to take the one that's closest to the x-axis, so in this case this one wins out. Now we can go ahead and find the angle to the x-axis and return it. Note that this time it's going to be a negative number. Now just by looking at this, you can see that the angle we are getting out is not the same as the angle we're putting in. Now we turn our attention to tan. It turns out that the angle I've chosen isn't a very good angle to demonstrate how tan works, so I'll just go ahead and change the angle quickly. This time I've used an angle of 6 pi on 7, so let me just go ahead and write down its coordinates. Remember that you can get the gradient by dividing the y and x coordinates, but we can also visualize it with this line. Now again, the inverse tan function just gets this gradient as an input, and because it doesn't have any other information, it also has 2 possible points. Now the inverse tan function also picks the angle that's the closest to the x-axis, which I'll go ahead and draw now. Now as you can see, the inverse tan function also has the same quirk. We don't get the same angle out that we put in. Now let's do a full example together just to make sure that you know how to do this. If we wanted to solve for the angle for when sine theta equals 0.5, since there are 2 possible answers, we need a bit more information. So suppose I told you that the cos of theta was negative. First, let's bring in our calculator. The first thing we're going to do is to take the sine inverse of both sides. Now we can cross out sine and sine inverse on the left-hand side, but conditions are going to apply. So that means theta is just the arcsine of 0.5. Now I'll add a really quick and really sketchy unit circle. Remembering that the x-coordinate is the same thing as cos, we were told that cos of theta is less than 0, so the x-coordinate of our point also has to be less than 0. Remember, the arcsine of 0.5 finds the angle when the y-coordinate is equal to 0.5. When we type the arcsine of 0.5, we got the angle for the closest point, but in this case this is not the point we want. Now to get the angle for this point, we take the angle of a semicircle and then we go ahead and we subtract this angle, as I'll show you now. As you can see, to get to the point that we want, we start at the x-axis, go forward by pi, and then come back by the angle in our calculator. Now we can go ahead and type this into our calculator. Now if we go ahead and divide this value by pi as well, we can write this in terms of radians. I'm not going to show that calculation, but I'll just write the result. Now this is our final answer. You can go ahead and try typing it into sine and cos to make sure both of these conditions are true. Now I'll just go ahead and get rid of this problem to make one final note. I just want to have a quick word on our notation for a moment. We very frequently want to raise trigonometric functions to some power. So we're allowed to write this power over here to avoid having to write this extra pair of brackets. However, if this power is -1, this actually causes a little bit of ambiguity. If we allow this to be the inverse sign, you have to realize that that's not the same as the reciprocal of sine. If you don't believe me, try picking a random value for x and subbing both sides into your calculator. You'll see that they're not the same. So we get around this problem by defining the inverse functions as arcsine, arccos, and arctan, as we've already said. Now to fix the problem on the left-hand side, we define the reciprocal functions, which you're going to see a lot of later on. Now this is an unfortunate choice of notation. Maybe we should have just not allowed this in the first place to avoid all of this. However, these are the common functions that you have to be familiar with, and I think once you've used them a few times, it won't be so bad. And now with this, we've completed our discussion on the inverse trig functions.